Thank you, Peter. So please let me know if there aren't any technical problems. Would be kind of a surprise if there would be none. But yeah, I hope that you can hear me appropriately. Okay, so my talk is not about some kind of special spaces. So what I want to discuss is kind of a general phenomenon. And the general question that one might ask is, if I want to approximate, then we all can maybe imagine an optimal method, so optimal information, optimal nonlinear, linear methods, whatever, but that's quite impractical, as we know, right? That's a basic topic of approximation theory, and in practical, so in applications, that's not very useful because we don't know the algorithm, we don't know the information, and so on. And the thing we really want to have, basically, is some special information and special algorithms that might be implementable. And what I want to present today is a joint work with David Krieg and with prior work of several other guys. I will mention that in a suitable situation that shows that function values are almost optimal for L2 approximation. And that's in a very general setting under a very natural assumption. So let me go through what I mean. No, I cannot. Oh, yeah, okay. So in general, what is it about approximation? I think we all know what I want to do here, but let me say it at least once, okay? Because also the other talks of David and Matthias today will go in precisely the same direction. So we want to compute an L2 approximation, or say any approximation of some f in a class, say big F, based on a preferably small number of informations. And the reason for that are manifold. So first of all, we might not know f and just have measurements. And the second, which is, say, nowadays much more popular than it was 20 years ago, is we basically know f explicitly in a mathematical sense, but we cannot work with this f because how to work with it on a computer, right? It's like working with an irrational number. Maybe we all know that a computer can not represent that in a precise manner. So maybe we want to compress it and we have some computing issues. We want to do anything with it, right? And this means it's also interesting to do an approximation with a small. So why is it all the time written here that I'm talking? I'm a bit afraid that this will at the end kill something. But yeah, perfect. Thanks. Okay, and the question now, if we talk about compression, if we talk about recovery or whatever, is what is information? So maybe well, what is information, and what information is allowed, and is this choice really important? These are the general questions we might have in mind. And just to say it in advance, so this F element, this big F, is kind of, we have some a priori knowledge, so some smoothness, some integrability, whatever. Okay, so during this talk, let me say what the general setting is. The general setting is we have an arbitrary measure space. We have an arbitrary, we take the L2 over this measure space, so the set of square integrable functions with respect to this measure. And we have a separable metric space, which is compactly embedded into L2. And since this assumption, although it's general, let me give some examples that basically fit everything that I will discuss later. So one example would be we take D and the measure to be arbitrary. You might even think of sequence spaces. You might think on probability spaces, whatever. So it's not even required that mu has finite measure. And F is the unit ball of an separable normed space. Okay, so you have a norm, you have this embedding condition here, and it's separable with respect to this norm. So at the end, this is a typical example. And the second one, which is much easier to imagine, is assume you have a finite measure, so Lebesgue measure on a compact set. So you have a finite measure on a compact set, and F is just, so every element of F is a continuous function. So this is maybe one, it's easy to imagine. And this also satisfies the general assumption we have here. Yeah, embedding means that the identity is injective and compact, just if you want to check that, but. Okay, what is an information? An information is just a linear functional. Okay, that's our assumption. So if you have a better idea of a definition for an information, please, we could discuss that. But I think it's just natural. So we have an arbitrary linear functional defined on our class big F, and the CF is then one information. Okay, and we might ask how many information do we need to know f up to a certain error. And it's clearly an interesting question. That's approximation theory. But if you talk about applications and special cases, then in general, we do not have access to arbitrary functionals, and that's not what we are doing. Usually we consider Fourier coefficients or whatever, or certain expectations. So what we have is we fix in advance in our application a class of admissible information. So really a subset of the dual space here. And this could be certain expectations, could be coefficients with respect to a given basis. But what we will discuss mostly here, but there will also be something in the last part of my talk, we will mostly talk about function values. Okay? It's just we want to compute function values. So a warning here, clearly not in every space function values are well defined. So of course we need some additional assumptions here. Okay, so what do we do with this information? So assume we have given some n informations, and if you want to, you might always think about function values. So C1 is just the evaluation at a point x1 and so on. And what we then do is we study linear algorithms. So our algorithm is specified precisely by a Ci, given Ci, and given phi I. And this is now our reconstruction algorithm. We have n information, we build them together in a linear way, and that's a linear algorithm. And also for most of the talk, I'm only discussing linear algorithms because for some extent surprising, linear algorithms are optimal up to logarithms, so up to logs. We will see the results later. So linear algorithms are also enough here. And what we want to bound is the worst case error. Let's say we have still a fixed algorithm, then the worst case error is just the error that I'm doing for a specific f, and now I take the supremum of our class big F, which might be a unit ball in a non-space. So that's just the definition of the worst case error here. But yeah, as I write here, several other settings are possible. So L1 approximation, L infinity, all this stuff, or maybe even another setting like worst case error. You could also discuss average case error, randomized error. Okay, and what we want to study, as I told you, I don't have arbitrary information, I have some special information. And the special information here is maybe function values. So let us define the sampling numbers, Gn of f, which is just, as you see here, the worst case error of an algorithm that only uses function values. But now we take the best points and the best functions, okay? So this here is the minimal error I can achieve with n function values. Okay? It's not constructive. This quantity itself is not constructive because I don't know the x and I don't know the phi. But as our result will show, I will give you so to some extent explicit algorithm, and also so I will give you some explicit algorithm here. And we want to know how small this can be, but this makes only sense if we have a comparison, so to say, and we compare that with the approximation numbers, which are also called linear width. So be very precise, these are not the approximation numbers because approximation numbers are for operators, whatever. So the linear width here is the same quantity as above, but now we really allow arbitrary linear information, okay? So these are the two different settings here. An of f is the minimal error that can be achieved by a linear algorithm that uses arbitrary information, and the sampling numbers is the best we can do with function values. So I think the AMs, the approximation numbers, most of us know that, so they are well understood. And usually the GNs are harder to analyze, even in specific cases, but in a general setting, there are not many results known for. So what we clearly have is that the approximation numbers are smaller than the sampling numbers whenever point evaluation is a continuous linear functional. And then it's that the set of function evaluation is just a subset. And so we take the infimum of a smaller set of information, and so that's larger. But the question is, how large can this distance be? It might be a general question. And again, let me say that we would like to make, so how large can this be, but not for specific examples. We want to have some general theory around. Maybe the only thing we know is the decay of the approximation numbers. And we want to know what then happens with the sampling numbers. That's just our general question. One might ask if this is interesting or not. It's up to everyone to decide that. But I think it's a natural assumption. We know that we can compress something with arbitrary info, with arbitrary algorithms. And now I want to see what happens if I only have function values available. Okay, so what were the earlier results? And they're already more than 10 years old here, but basically that's the only thing that was known for the last years. Because this is not for examples, it's really the only assumption you do is you assume some decay on the approximation numbers. Okay? So there is first one positive result, and this positive result is due to Francis Kuo, Greg Wasilkowski, and Henry Wozniakowski, with earlier work, I think 1 year earlier, of Wasilkowski and Wozniakowski only. And they proved that assuming that the class F is a unit ball of a Hilbert space, remember it must be compactly embedded into some L2, but it's just in Hilbert space here, such that the approximation numbers decay with some polynomial decay, n to the minus alpha, general assumption here, then what we get is that the sampling numbers also decay, but the rate of convergence might be only half of that. Okay, that's what was known. Even this was a surprise. Think about that. That just means you cannot find any space such that the approximation numbers decay like, say, 1 over n, but you don't have maybe any decay on the sampling numbers, all right? So function values are always helpful, at least if the polynomial decay is larger than 1/2. But also there is a negative result, and this negative result is, yeah?
So do you have to assume that it's a reproducing kernel Hilbert space or something like that? Because if you're taking function values,
under this assumption it is, because the sampling, the approximation numbers are just the singular values of the embedding, and since you have this condition, the approximation numbers are square summable, so this is a reproducing kernel Hilbert space. Okay, in the same way I could write a reproducing kernel Hilbert space because that's just what it is.
You're taking point.
Yeah. So under this assumption, every Hilbert space under this assumption is a reproducing kernel Hilbert space. Yeah. Okay. So, but to make sure, a reproducing kernel Hilbert space does not mean that function values are bounded. It just means that function evaluation is a continuous functional. That's it. Okay. Okay, but as I said, here's also a negative result, and this is basically due to Dima's question, I would say, because these spaces. So if the approximation numbers are not square summable, then there exists an Hilbert space with exactly this an as decay for the approximation numbers for all n, but the sampling numbers basically do not decay. So they decay slower than, say, 1 over log n, or even so. So you can do that for an arbitrary sequence going to infinity here. So this already shows that approximation numbers being in L2 seems to be an important quantity. And for Hilbert spaces, that's not a surprise because that's precisely the border of having compact embedding. So having this reproducing property or not. Okay, so these are the two earlier results. And there was, I think, nothing in the last 10 years, no progress, until we started again for studying random information. And to say a little bit to the story, our original goal was not to work on this. Our original goal was, we haven't thought that we are able to improve that with this we had in mind. We wanted to understand how good random information is. So we just wanted to know, assume our information is not the best one in any class, assume you have given a class any probability measure on it, we take random information, and is random information as good as the best one? And what turned out, and this was a surprise to us and maybe also to other guys, is that we basically found out that random information is optimal, almost optimal. That's what the title of my talk. So instead of saying function values are almost optimal, I could in the same way have said random information is almost optimal. And that's this was really a surprise to us. Let me explain that. So these are the positive result and the negative result here. And you see we lose an order 1/2 here, which we don't want. So what then came was a kind of a very positive result, which has quite some history. I don't have the time now to discuss that. So there were several papers also of other guys. So Tino Ullrich is also related to that. So we are, yeah. So what we proved is the following result on the power of function values. Assume that f is like our general assumption, so a separable metric space of functions on some set D, point evaluation is continuous, then the sampling numbers can be upper bounded by some square root of log n times this sum here. And if you cannot really, if you don't see immediately what this means, this guy here is basically of the same order as an, as long as the sequence here is really inside L2. So it's not on the border of it's not almost summable. If AK is something like n to the minus alpha for alpha larger than 1/2, this sum here is just n to the minus alpha. But okay, we needed some p summability here, and let me say here it's not for Hilbert spaces. Right? So we were even expecting basically that the result, these earlier nice results here, only hold for Hilbert spaces, and maybe there must be something worse if you take different classes. But here, basically, you could do that for arbitrary sets. Right? You don't even need that a set is a vector space. It's a metric space, so it can be an arbitrary set with a metric on it. That's, for us, it was kind of a surprise. And to prove such a result, you had already realized that you need random techniques for that, because otherwise, all the techniques you are using uses any more structure than that. That's the surprising fact here. And let me say that if you take a Hilbert space, then you can actually do p equals 2 here. And we still do not know if this works for Hilbert space, for non-Hilbert spaces also. I guess no. And for guys who know all the results in their round, it's a similar situation like with the Rademacher-Menschow theorem, where basically you need some extra logarithmic decay. Otherwise, you can prove that even Fourier series do not converge. I think there is some relation. I haven't found that by now, but I think something is there. Okay, so you see, that's a very positive result. What was a very negative result that appeared only some months ago, though it was proven without me here, but same group almost. So Eike Hinrichs, David Krieg, Erich Nowak, and Jan Wieberei proved that there is a Hilbert space. For any sequence in L2, there is a unit ball of a Hilbert space, of a reproducing kernel Hilbert space, with this decay of approximation numbers, but the sampling numbers really have a lower bound like that for infinitely many n. Right? So this shows that the result that was proven by David and myself is essentially best possible, up to some log factors or some boundary, some limiting cases and so on. So the question in this result here is this lower bound true for all n? And yeah, that's yes. The answer is yes if the sequence is regular enough. So for most examples we have, that's just yes. But at the moment, we don't know if you find an example where this holds really for every n. So one might think that there is also you can improve that a little bit, but we don't guess. We don't conjecture that. Okay, and is this the worst possible behavior? That's the next question, even for general f, because if you look back to the positive result, there is some log n here. And we really don't know if this log n appears because of our random technique, or if there is if it's really necessary to be there. At the moment, we really don't know. And I don't have any conjectures about that, by the way. That's not clear to me. Okay, just to give a corollary to see better what these results imply for specific sequences. So assume that f is an arbitrary class, an arbitrary subset of L2, under the general conditions I gave, such that the decay of the approximation numbers is n to the minus alpha times log to the beta n, right? So even with the logarithmic precision we have here, where alpha is larger than 1/2 and beta is arbitrary, so this sequence is in L2, then we get that you can basically do the same with function values. The only thing you lose is some square root of log n here. Right? And for applications, you maybe don't care about square root of logs. So this basically means function values are as good as approximation numbers if you already know that the approximation numbers decay fast enough. And even more, if you now go to boundary cases, this follows from the very negative result. If you now take the approximation numbers of this kind, so really 1 over square root of n times log to the beta, with beta smaller than minus 1/2, so again, that's beta minus smaller minus 1/2 ensures that the approximation numbers are square summable, then we get that there is a Hilbert space such that the rate of convergence is precisely that. So you see that you really have to lose this square root of log if you just consider a general setting. And about the second result, or even the very negative result, David Krieg will give a talk later. He gives some explanation on that. But let me say that the Hilbert space you have here is one all of us have worked with already. Okay, that's just a univariate Sobolev space. But David will go into detail on that. Okay, so what is the drawback? As I said in the beginning, the upper bounds are existence results. So we don't know good sampling points, and we even for specific f, and if you talk about general f, what even does it mean? You don't know what your set D is, right? So what does it mean to have good sampling points? But what we can do is we could weaken the bound a little bit, and then we can prove that IID points work with high probability, and we even know an explicit algorithm. And what do I mean with IID points? I don't mean that you have for every f some new points. This would be a randomized setting. I draw random points, and with probability, with very high probability, these points work for every f in my class. It's still a deterministic worst case bound, but it holds with high probability, right? That's more like a data science setting. That's not so. This setting is not so usual in our community, but it's popular in the world by now. Okay, so what is the algorithm we have? The algorithm we have is just a least squares algorithm, probably the oldest known algorithm for approximation. Yeah, okay. So what is the setting here? So we have some orthonormal basis. We take some Vn, which is just the span of the first n functions here, and the algorithm is then given just as the best approximation in this class Vn, which minimizes this kind of pointwise error. So just a discrete L2 minimization here. Yeah, G is from a finite dimensional space, so that's just least squares. And the only thing we need to fix here is the class Vn, the points xi, and these weights here. Okay, these three things specify the algorithm. And yeah, and that's what we basically done. So assume that this B1 up to so B1, B2, and so on is a good orthonormal basis. I don't have, yeah, okay, I have the time to say that this is basically the eigenfunctions of the identity, right? So they come from the singular value decomposition. If you know them, then you know them. But so for example, for Sobolev spaces on a periodic, it's just a trigonometric system. That's the good orthonormal basis here. And the density is given like that. And here it's important to say that if you skip this part here at the end, then this is just the so-called Christoffel function. Many people know that. There are many results on that. And it's known that sampling with respect to this Christoffel function is in many cases good, right, and almost optimal. But I think, and I'm relatively sure, that this adaptation of this Christoffel function by taking also into account all infinitely many basis functions here was basically invented by us. And so this at the end works then for arbitrary spaces. This was maybe the most important idea here. Okay, yeah, this omega k, the wk can be given explicitly also. Okay, and what is the result then? The very general result. The very general result we have, and that's from this we can get all our results. Assume f is an arbitrary countable subset of L2, and x1 to xn are independently drawn with this. Then we have this bound here, the same like we had before without this log n in front, but note that we need now, this big N is now of the order n log n. Okay, so if we make a logarithmic oversampling, then random points really do the best that we can do. Okay, so it's just logarithmically more points, and we get that. And note, there is not any assumption on f here. The only assumption we need is the countability, right? And all the other separability and so on, we assumed then was just to bring that to infinite, so to uncountable sets. But that's like it's always been done with, yeah, with measurability and so on. Okay, so that's the result here. So let me give some comments on the proof. The random proof here uses eigenvalues of large random matrices, but not even very deep things. There is the results we are using there are well known for 10 years and are used in many areas. So it's just, you have a rank 1 matrix and you just take the sum of rank 1 matrices and you want to have some concentration there. and the concentration with respect to the eigenvalue. So that's well known. And the other thing, so coming from the random result with n log n points to the existence of n good points there, that's some kind of downsampling strategy, which is based on the famous solution of the Cadison-Singer problem. I will come to that on the next slide. So 2 more remarks. The same can be done with other classes of information. If I have time, I will discuss that very shortly. And the last comment here, we have similar results from nonlinear algorithms. So even if you now not want to take linear, if you want to allow nonlinear algorithms, which is from your application aspect, maybe not really interesting, they mostly use linear algorithms, but whatever, we can even prove a similar comparison for arbitrary nonlinear algorithms. So the picture in this respect is almost complete. We have just problems in the limiting cases. Okay, so this is the result I would like to show because I just think it's amazing and it will be applied quite often, I guess, in our community also. So this is the last step of our proof, and this uses, so this was first used by Nagel, Schäfer, and Ullrich that I already cited some slides ago. At least for our approximation problem, there had been some discretization results earlier, right? Okay, so what is this? This is basically Weaver's theorem, was called Weaver's conjecture until it was proven by Markus Spielmann and Srivastava. And this is just an amazing result, right? The result states the following. Assume you have big N, many n-dimensional vectors, all of them has a bound on the L2 norm here, such that you can approximate the L2 norm of an arbitrary vector just by these inner products. With big N, very large, you don't have to care what N is. N could be 2 to the power small n, right? It could be anything. If you know that you have that, then that's Weaver's theorem. You get that there exists a subset of optimal size, of optimal dimension, such that you have basically the same up to constants. This result is not even amazing. I would even say if you ask someone from 15 years ago, they would even not believe you that this is true, right? There were many people thinking that Weaver's conjecture is just wrong. But this result, it's an amazing result and a very, very powerful result, especially in our setting. Okay, so let me shortly discuss an example. I think I still have these. Yeah, sure. Okay, so what is the example most of us know about? And let me say that this is the interesting fact. Let me go back for a second. We proved that here for arbitrary sets or with the separability. I don't want to go back this far. Okay. So we have this for independent points, and somehow it was not. Who would conjecture that in the setting we are here, just taking n points independently drawn by any density, that at the end you get an almost sharp result, right? This is something strange. And the funny thing here is that even in very specific situations that are studied now for 50 years, we at the end improved all known results. And so let us check the Sobolev space with mixed smoothness. All of us know them, I think. If you are related to discrepancy on a torus or on the cube, then that's just the case s equal to 1. And so what we take is we take all functions such that their mixed derivative up to order s are in LP. Okay, that's the norm. And what is well known here is that if p is smaller than 2, then everything was known for quite some time. Okay, so that you have precisely this order, and the optimal algorithm are sparse grids. It's the Smoljac's algorithm, and that's known for many decades. Okay, for p is smaller than 2, everything is fine. For p larger than 2, we have the obvious lower bound that I already stated in the beginning. So approximation numbers are smaller, and you know the approximation numbers precisely. That's easy to compute here, right? So this was the lower bound, and the upper bound we get for these spaces is instead of, so the main order is the same, but in the logarithmic here, you get s plus 1/2 times d minus 1, right? So here instead of s, there is some s plus 1. So you have some additional log to the d minus 1/2. Which somehow also looks like a discrepancy thing, right? Okay, and all these upper bounds are achieved by sparse grids. And it was just the prevalent conjecture of many people. You might ask several people from Bonn who were working on that for quite some time, that they thought Smoljak is optimal in this case. And what you have to do to find the optimal order is prove lower bounds. I know many people who try to prove lower bounds for several years, right? And at the end, it turned out that this is wrong, this conjecture. So it's not basically our result that should be fair. So in the case P equals 2, this was proven by Tino, Ullrich, and colleagues. And yeah, for P larger than 2, that's just an easy embedding. So let me say, skip that and just right here, we know now. So it's not our result here, basically. But yeah, let me come to that in the next slide. So the sampling numbers are now upper bounded by, again, same polynomial order, clear. Then there is the s to the d minus 1, which comes from the approximation numbers. We cannot do better than that. And then there is the additional square root of log n, I was already telling you, right? Okay. So this is now the upper bound we know. And to be a little bit more precise on our constructive algorithm, one has to say that in these spaces, the good orthonormal bases are just a trigonometric system. So this trigonometric system is uniformly bounded, right? And if you look at our density that I gave you, if all these bk are uniformly bounded, this means that the density is uniformly bounded. So essentially, you can just sample IID. Okay. So what we are doing is we just sample with the uniform density, independent and uniformly distributed in the torus. And we take n points, and then with n points just thrown into the cube, we still get this bound here. So as I told you, you need some logarithmic oversampling, which is now hidden here. So we get n to the minus s times log to the s times d times n. Okay? So this result is basically due to David and myself, and Tino and colleagues then improved that by using this downsampling procedure. So okay, that's the purely random result. Let me say, Cadis and Singer and Weaver theorem, if you want to get the good point set, that's very not constructive. Basically, most likely you will never can do that on a computer. That's only existence result. And yeah, but this is just purely constructive. Okay? So as a comparison, note here is s times d. The best bound we can get is s times d minus 1 plus 1/2. And Smoljak only achieves s plus 1/2 times d minus 1. And you might already see that in dimension, that if the dimension grows, our bound is better than Smoljak already. So this means we have with high probability this, and this is of a better order than sparse grids if d is larger than 2 times s plus 1. And the basic open question is a very interesting open question. What are optimal points in this situation? Right? So sparse grids is something like that. And these are random points. And it's not only that we know that optimal points are somehow hidden in this cloud of points here. We basically know that this set of points is already better than sparse grids. This, I think, is a surprising thing. So many people study these spaces, and we still have no idea here. Okay, so I still have some. Yeah, maybe I go shortly over that. You can do precisely the same for other classes of information. So function values were not special. As I told you, it's random stuff. So there is really nothing special about function values. You need only some structure. So if you have a given set of admissible information, call it lambda, and that's the minimal error that you can achieve with this information, and you might compare this to the approximation numbers. And what the result is, assuming that there exists a measure on the class of information such that you can recover the L2 inner product. But that's really not a surprise, this result, right? If you somehow have a feeling on the proof. So if you can recover the L2 inner product with some measure here, then sampling with this measure on lambda gives you basically the same result than we had before. And again, downsampling works in the same way. So to give you one interesting example, I think, assume you take an arbitrary orthonormal basis. You have your class F, and the optimal basis is very strange. You don't know that, right? But you maybe are on the cube, and maybe you really like the Haas system. So you decide, I just want to compute the inner products with the Haas system because I just like that. And I tell you that's not so worse. That cannot be very worse. Because if you take an arbitrary orthonormal basis, you can obviously recover the L2 inner product, right? And note that in this situation, because that's just an orthonormal basis of L2, f does not appear at all in this formulation. So it doesn't matter what f is. The only thing that matters is you must be compactly embedded into L2, and you take an orthonormal basis from this L2. So this is completely independent of f. And this just means that your favorite L2 basis gives you almost optimal information, and you can use projection with that, and you only use the square root of a log under the assumption that there is any means to approximate that, so that the optimal information is good. Okay, yeah, the algorithm is still least squares and density. Yeah, that's not so important. That's all I want to say. Thank you very much.